In lesson 35, we want to talk about ratios and rates. Now, ratios and rates do look a lot like fractions, and they sort of act like fractions, and we do the same math. Math doesn't change just because we use numbers for different things. We still, the principles still stay the same. But what a ratio is really a comparison of two different quantities to each other. A rate will compare different types of quantities. You're familiar with miles per gallon. Miles is one type of quantity, gallons is another, and that's really a rate. Ounces per cent is another one. Ounces is a different quantity from cents, and we'll see, we compare those when we're shopping for food and things. And then let's look at, we can get the ratios to the simplest form by using fractions is what we do. So when we say, in example number 1, 25 to, the word to, 150, what we're really saying is 25 to 150. And when we draw the line for the fraction, we say the word to. And that's how we read a rate. We're comparing 25 to 150. Now, we can reduce that, of course. So that rate can be simplified. We would divide both by 25. When I divide 25 by 25, it becomes a 1. And I divide the denominator by 25, and it becomes a 6. So that rate is really the same as 1 to 6. Example 2 is 8.1 to 10. Now, we never leave a decimal in a ratio or a ratio. And so what we have to do is we have to move that decimal one place to the right. When I do that, it becomes 81, but I also have to move the decimal in the denominator one place to the right. What I've actually done is multiplied both of these numbers times the number 10, which is fine. I can always multiply the top and the bottom of a fraction by the same number. So my ratio is really 81 to 100 instead of 8.1 to 10. That's the way we would write it. Example 3, 6 ounces to 16 ounces. And of course, we need to reduce it. Divide both of them by 2, because I think that's the common denominator we can find, and we would have 3 to 8, 3 to 8. 6 to 16 is the same as 3 to 8. What if we have, though, weird sort of ratios? What if we have relationships like 3 1/3 to 4 1/6, as in example 4? Well, this is where we get to do a little work, and it's sort of fun work. It's the same thing we've done with complex fractions. We would write this problem as 3 1/3 over 4 1/6. And of course, you know we're not going to leave it like that. We're going to change both of those numbers, both of those fractions, mixed numbers, into improper fractions. 3 1/3 will be 3 times 3, which is 9, plus 1. It's going to be 10 over the denominator of 3. That's our top fraction, our numerator in a complex fraction. And then 4 1/6 is going to be 4 times 6, 24 plus 1, or 25 sixths. Now, what do I know I can do now? With a complex fraction, it's really just numerator divided by denominator, right? So I can still keep simplifying this. I can say 10/3 divided by 25 sixths. It's getting better. I don't ever divide fractions, right? I multiply by the opposite, the reciprocal. So let's change it. And let's say down here 10/3 times the opposite. Let's flip it. 6 over 25. Well, now when we multiply fractions, we can cross-reduce. So we still haven't finished simplifying. I can reduce these by dividing 6 and 3 by 3. I end up with 2 and 1. And 10 and 25 can both be divided by 5, 2 and 5. Now let's multiply numerators. 2 times 2 is 2, and 1 times 5 is 5. And my final fraction, 2/5. So 3 1/3 is to 4 1/6. It's the same as 2 to 5. That's the final reduced ratio. So all we did was everything we've ever done with complex fractions. Let's do it again for example number 5. If you feel comfortable, go ahead and stop the tape and work number 5 by yourself, and then check your work. First, I'm going to write the complex fraction, 3 1/3 to 12 1/4. Then I'm going to change both of those to improper fractions. 3 times 3 plus 1, 9/3. And the bottom fraction, 12 times 4 is 48, plus 1, 49 fourths. Let's fix my problem here. I meant to write 3 1/2. Okay, so that's not going to be 9/3. It's going to be halves, and it's going to be 3 times 2 is 6 plus 1. That's going to be 7/2. Okay, I hope you can read that. 7/2. All right, let's change this into a division problem. 7/2 divided by 49/4. Now, we're going to turn that around. The first fraction stays the same. The second one flips, and we change it to multiplication. So it's 7/2 times 4 49ths. Let's cross-reduce. We can only cross-reduce when we are multiplying two fractions, remember. So 2 will go into both of these numbers, and 7 will go into both of these numbers. And then I can multiply numerators, 1 times 2, denominators, 1 times 7, and my final reduced ratio is 2/7, or 2 to 7. Now, why do we look at ratios? We look at things called unit rates to see which is the better buy. A unit rate is how much per one something. If I have 12 ounces for $2.29, and I want to know if that's a better buy than 8 ounces for $1.49, I have to actually find out how much it costs for 1 ounce. I can't really compare the 12 and the 8 in my head, but I can compare 1 ounce. So I'm going to take $2.29, and I'm going to divide it by those 12 ounces to find out how much it is per 1 ounce, how much 1 ounce cost. I'll place my decimal. I'll start doing the division. 12 goes into 22 one time. And when I subtract, I see I have 109. Well, that would be 9 times 12 would be 108. And then I could keep on going, but do I need to? So it's really 19 cents per ounce, the first one. Let's see what the 8 ounces is. I've got $1.49, and I'm going to divide that by 8 ounces. This will give me how much it is per 1 ounce. Well, 8 will go into 14 one time. I'm going to subtract, bring down, and 8 will go into the 69. Well, it's going to go 8 times. So already I have a different digit, don't I? I have 18 cents for the 8 ounces. I have 19 cents for the 12 ounces. The 8 ounce is the better buy.